In this video, I measured the gravitational acceleration of Teyvat was approximately 20.85 meters per second squared, and that the terminal velocity was 35.7 meters per second. But was I wrong? Hello, Count Sacke here, back with another Genshin Impact video. In my measuring gravity video, I was able to determine a way to verify the 20.85 meters per second squared gravitational acceleration. However, I wasn't very rigorous about it at all, and I didn't even have a way to experimentally check if the terminal velocity was correct. This video will only really focus on the gravitational acceleration aspect. For the terminal velocity, that will be in a follow-up video, so be sure to subscribe if you don't want to miss that one. And while you're at it, you can also click the like button. Anyway, so how can we really check if my value is correct? For that, we'll need to talk about curve fitting. In the previous video, I did an experiment where I would measure the time taken to reach the ground at heights from 0 to 20 meters by increments of 0.5 meters. I then took the times measured and plotted them on a displacement versus time graph and a time versus displacement, or height graph. I drew a quadratic curve using g equals 20.85 meters per second squared, and it seemed to match up with the points from the experiment quite nicely. Now, here's the big question. Could we find a better value for the gravitational acceleration that matches the data points? However, what does it mean to find the best value? In our case, we want to estimate a value for g that best matches the data. I'll call this estimator g hat. Now, how do we calculate it? Hold on, before we can answer that question, we first need to establish what our model, or equations, we should use as for our basis. From the kinematic equations, we know that while the object is accelerating, the height is modeled by the following equation. H is equal to a function of the time squared, and that is equal to g times t squared divided by 2, where g divided by 2 is a constant coefficient. If we were to generalize this, it would become y is equal to f of x, which is equal to beta times x, where beta is a constant coefficient. Let's say that we have n samples of data. We could collect these values and put them into vectors. This means that we have the following expression. Vector y is equal to the constant beta times vector x plus vector epsilon. Now, I'm gonna stop saying vector so on. Just know that if I put an arrowhead over it, that's a vector. Okay, so epsilon is an error term to account that beta times x won't exactly give you y. This error term is how we calculate the best estimator for beta, which is beta hat, and in turn, g hat. In other words, we want an estimator for beta, which we called beta hat, that minimizes epsilon, or the error. To calculate beta hat, we can use the method of least squares. Now, there's a bit of calculus involved with this, but the gist of this is that you calculate the square error and use derivatives to find the minimum, which is done by setting the derivative to 0. You do some algebra after that, and you get an equation. From the least squares method, we can see that the estimators with the minimum error for beta and y are the following. Beta is equal to the inverse of x transpose times x multiplied by x transpose times y. Then y hat is equal to beta hat times x. Going back to our case, our equation takes the form of h is equal to a function of the time squared, or it's equal to gt squared divided by 2. If we put this back in the general case, y is equal to a function of x squared. So y equals beta times x squared. This implies that beta hat is equal to g hat divided by 2, or g hat is equal to 2 times beta hat. Our equation for beta hat does change since our input variable is now x squared. This means that our x vector is now equal to this. From here, it is implied that beta hat can be calculated as the following. Beta hat is equal to the summation of x sub I squared times y sub I, and that is divided by the summation of x sub I to the 4th power. After going through all of the calculations, we obtain the following estimators. Beta hat is equal to 10.198 meters per second squared, or if we convert it to g, we get that the best estimation of the gravitational acceleration is equal to 20.397 meters per second squared. Just looking at it, 20.85 meters per second squared isn't far off. However, is it statistically close enough, or is there a significant difference? When you speculate about something, you're making a hypothesis. I go into more detail about the scientific method in this video. For our case, we're speculating about what the gravitational acceleration is. In statistics, there are 2 types of hypotheses, the null hypothesis, H0, and the alternative hypothesis, HA or H1. The null hypothesis is typically assigned as the generally accepted, default, or most likely statement. For some guidance in choosing a null hypothesis, it is usually the statement that you want to test. The alternative hypothesis is the opposite of whatever the null hypothesis is. This is to make sure that the two account for all possible scenarios. For example, if H0 states that the average height of Genshin characters is within 4 to 5 feet, then this means that HA must say that the average height of characters is shorter than 4 feet or taller than 5 feet. In our case, I'll define G0 as the hypothesized value for the gravitational acceleration, which is 20.85 meters per second squared. This means that the null and alternative hypotheses are the following. G is equal to G0 and G is not equal to G0, respectively. The concept of hypothesis testing is that we have a statement that we want to test and see if we can rule it out. There are 4 possible scenarios when evaluating hypotheses. 1. A true hypothesis was correctly deemed as true. 2. A false hypothesis was correctly deemed as false. 3. A type 1 error, which is that a true hypothesis was incorrectly deemed as false. And lastly, 4. A type 2 error, which is where a false hypothesis was incorrectly deemed as true. In statistics, we usually focus on either the type 1 or type 2 error. Also, we like to put it into the perspective of the null hypothesis. For a type 1 error, it is incorrectly rejecting a true null hypothesis, while for a type 2 error, it's incorrectly failing to reject a false null hypothesis. It's important to know that for type 1 errors, the null hypothesis is assumed to be true. With type 2 errors, it is assumed to be false. This could help you identify what your null hypothesis should be. For our case, we have a set of data which can be used to compute for the best possible value for G, which is G hat. The goal is to see that if we decided to reject the notion that G hat is truly equal to G0, what is the probability that we would commit a type 1 error? This probability is the p-value. The definition that I think makes the most sense for the p-value is this. The p-value is the chance that based on your data, it would lead you to incorrectly reject a true null hypothesis. I want to point out that this definition is not one taught in conventional statistics classes. Here are the 2 definitions I've learned. It is the probability of obtaining the data collected or something more extreme, assuming that the null hypothesis is true. Or alternatively, it is the smallest level of significance that would lead to the rejection of h0 from a given data. The first one is the equation for the p-value interpreted literally. However, I personally find this equation very unsatisfactory from an intuitive level. I was always confused with it and never liked it at all. Sure, it literally tells you how you would calculate the p-value, but it didn't really give me an understanding of why we use it or what it is for. The second one I think is better conceptually for understanding how we apply the p-value and use it to judge significance. If there's a small chance of committing a type 1 error or incorrectly rejecting a true null hypothesis, it implies that h0 is likely to be false. Therefore, we reject the null hypothesis. If you concluded that you would not reject h0, you would be very likely incorrectly failing to reject it. If there's a big chance of incorrectly rejecting a true null hypothesis, that implies that h0 is more likely to be actually true. Therefore, we would fail to reject the null hypothesis. If you concluded that you would reject h0, you would be very likely incorrectly rejecting it. If you're wondering how my personal definition relates to the first definition I showed taught in conventional statistics courses, I'll try to explain, but I'll be honest, it's very confusing. The question is this: how is the probability of getting a type 1 error based on data related to the probability of getting more extreme data than what was observed? To understand this question, it is important to remember that we're assuming that the null hypothesis is truly correct. This means that we should expect the collected data would match what the null hypothesis states. Extreme data refers to the data that is very unlikely compared to other possibilities. From the perspective that the null hypothesis is true, the extreme data is unlikely. However, if your data is extreme, it puts that into question. Perhaps the data that was obtained is actually more likely than what the null hypothesis suggests. Therefore, it lowers the probability that choosing to reject the null hypothesis leads to a type 1 error. The probability of getting the data you'd collected, or something more extreme, and the probability of a type 1 error based on the observed data are literally the same. It's unlikely that you'd get the more extreme data, but you did anyway. So it's unlikely that choosing to reject the null hypothesis is irrational. On the other hand, if you see that there is a lot more higher chance of getting more extreme data, the probability of a type 1 error would be very high. That would mean that you can't reject it, otherwise you would likely be committing a type 1 error or incorrectly rejecting a true null hypothesis. Of course, this assumes that your data is reliable and actually trustworthy. If you want a rundown of basic qualities of trustworthy data, I have a video called Analyzing 150 Million Plus Wishes to Find the Average Pity. I also go over important statistical terms like population and sample, so if those sound unfamiliar to you, I recommend that you watch it. I really encourage you to take the time to understand what I've mentioned. They make a lot of the reasoning behind why the results that we see lead to the specific conclusions that are drawn. With all that we've said so far, there is one very important question that we need to consider. What determines the tipping point between rejecting and not rejecting? Some hypotheses would require a smaller probability of error to reject than others. For instance, you probably want to make sure that medications have a very high level of scrutiny. You would assume that the null hypothesis is that the medication is not effective. Now, obviously, we don't want to say that the medication is effective when it's actually not. So, requiring a very, very low chance of a type 1 error for medications is probably very important. In statistics, we define the tipping point that we were referring to as the level of significance or significance level, denoted as alpha. The significance level is defined as the smallest allowable probability where choosing to reject the null hypothesis with anything more likely would reasonably result in a type 1 error. This means that if your data suggests that the probability of a type 1 error is greater than the significance level, it's within reason that rejecting the null hypothesis would likely result in a type 1 error. On the other hand, if your data suggests that the probability of a type 1 error is less than alpha, it's likely you won't commit a type 1 error when rejecting the null hypothesis. In short, the significance level can be interpreted as the threshold probability where if the p-value is smaller than it, there's statistically significant evidence to reasonably reject h0. When alpha is closer to 1 or 100%, it means that you have more faith in the alternative hypothesis and can more easily reject the null hypothesis. It could also mean that the null hypothesis is precise and stricter. When alpha is closer to 0 or 0%, it means that you have more faith in the null hypothesis being true. We are literally free to choose whatever probability we want for alpha. Just remember that you need to specifically state what significance level you're using. You can't just say there's statistical significance. Statistical significance needs a level of significance to know where the line between significant and insignificant is. The convention is that if there isn't a specific value that you have in mind, choose alpha is equal to 0.05 or 5%. However, it really depends. Maybe for institutions and products there are standardized values for alpha, but being honest, it's completely subjective. The term significant is a subjective term after all, so naturally, it depends on what you personally think the level of significance should be. To recap on our situation, the null hypothesis that we established is that G is equal to G0, and the alternative hypothesis is that G is not equal to G0, where G0 is equal to 20.85 meters per second squared. For me, since I have faith in the null hypothesis, I'll choose an alpha of 1%. Recall from earlier that to see if there's a statistically significant difference between G hat and G0, we need the level of significance, yes, but we also need to calculate the p-value. There are two types of statistical tests that we can use to do this, the z-test or the t-test. Z-tests and t-tests appear to be pretty similar as they're both used to see if there's a statistically significant difference between two populations. However, they're actually quite different. A z-test can be used if you know what the population variance is, or if you have a high enough sample count to assume that your sample variance is close enough to the population variance. We obviously have no idea what the variance for the gravitational acceleration could be, so we can't use a z-test. This means that we're only left with the t-test, and it is definitely much more appropriate, specifically a two-tailed t-test. We're using two-tailed because the gravitational acceleration could be greater or less than g. To calculate the p-value with a t-test, we need to compute the t-statistic or the t-score. The t-score is a measure of how different g hat and g0 are in terms of sample standard deviations. And these are the equations associated with the t-test. As can be seen here, these equations are quite something. I'm just going to have a computer do the computing for us. If you want to calculate it by hand, be my guest. Anyway, T0 is the t-statistic of our null hypothesis. SE of beta hat is the standard error of beta hat, or it's basically the standard deviation of beta hat. Here's the derivation of the standard error for beta hat. while we're here, we can also analytically see how well the model fits the data by calculating a value called r². The closer r² is to 1, the more accurately the curve fits the data. If r² is closer to 0, then the model doesn't match the data well. The equation for it is that r² is equal to 1 minus SSE divided by SST. And then SST can be calculated with this equation. That was a lot, so I'm going to summarize all of the necessary equations, and here they are on screen. After going through all of the calculations in the equations, these are my computed values. G hat is equal to 20.4005 meters per second squared. R² is equal to 0.9956 or 99.56%. The t-score was equal to negative 4.4969 and the p-value was 0.0054% with a g0 of 20.85 meters per second squared. Something to also note is that the r² with g0 is equal to 99.35%. However, if we remember, my level of significance was 1%. Now, because 0.0054% is less than 1%, this means we must reject my null hypothesis, so therefore, the gravitational acceleration of Teyvat is not equal to 20.85 meters per second squared. I have to say, I was actually very surprised. Despite the graphs looking very similar to each other while having a very similar r² coefficient, I mean it's 99.56 and 99.35%. I must reject my null hypothesis and conclude that the gravitational acceleration isn't likely to be 20.85 meters per second squared. The t-test I conducted shows that there is a statistically significant difference between g0 and g hat. I looked back at my original measurement data for the gravitational acceleration to try to make sense of everything. Something that caught my eye is how many frames it took for the player to hit the ground at a height of 5 meters. When looking at it deeper, I got this distribution. For most of my measured times taken to fall 5 meters, it took 42 frames to hit the ground. If I calculate the gravitational acceleration based on this value, I get that g is equal to 20.408 meters per second squared. This value is very close to g hat. So I personally now believe that the most likely value for the gravitational acceleration of Teyvat is 20.4 meters per second squared. I also took the time to analyze the margin of error in the acceleration with the old measurements. Using the method that I did, the error can be calculated with the following formula, which uses some basic Calculus 1 stuff, derivatives and all. The error in the gravitational acceleration is equal to 4 times the height divided by the time cubed times the error in the time. Assuming only a single frame of error for a height of 5 meters, which took about 41.606 frames, this error in the measured value came out to be 1 meter per second squared for the gravitational acceleration. So essentially with my old analysis, the gravitational acceleration had a value of 20.833 plus or minus 1 meter per second squared. Personally, I think that's a lot larger than I would like. That's also only assuming the minimum of a single frame of error. It could actually be larger. If you were to fall from a taller height, this error would actually decrease. That's why I recommended using a higher height in the last video. In conclusion, I conducted new experiments and analysis to check if the gravitational acceleration I obtained in the last video would be a good estimate for the actual value. A two-tailed t-test was used to see that a value of 20.85 meters per second squared had a statistically significant difference from the optimal value obtained via curve fitting. Instead, I found that the gravitational acceleration of Tevat is more likely to be 20.4 meters per second squared. With our new calculated gravitational acceleration, this now begs the question, what about the terminal velocity? Well, you can expect another follow-up on that one, so that's another video to look forward to. Be sure to subscribe so that you don't miss out on it. While I'm quite satisfied with the results I got, there's still room for improvement. For the displacement versus time graphs, it would be better to consider more samples of measured time per height. In this case, I only measured the time taken to reach the ground once. So basically, I started at a specific height, measured the time it took to fall that height, lowered it by 0.5, measured the time, again lowered by 0.5. Instead, you might want to consider doing something like maybe falling to the ground 3 times from the specific height, then you decrease the height, then measure the time 3 times again. So for every height, you have maybe 3 samples of time. So that could potentially get these more accurate. The methodology for the statistical analysis will remain exactly the same. You use the t-test, the p-value is calculated the same, so you should have the means to do so as long as you have access to Excel or Google Sheets. I really hope that you enjoyed this video. I tried to put a lot of clarity behind understanding hypothesis testing because I've always got confused with it. I remember spending many hours just pondering the concepts, trying to grasp them. So I hope that this video made things more clear. That's really about it for now, so thanks for watching and hope you've enjoyed.